I'm Dr. Munji, and today we're going to go over a review of shear stress. Today's video is going to go through an overview of shear, then we're going to derive or do a small derivation of the shear formula. Then we're going to talk about a few limitations of the shear formula that we derived. We're going to go over an example problem, and then I'm going to leave you with a practice problem to try what we learned today on your own. Let's start by talking about shear and straight members. And so primarily we're going to talk about beams. Beams support both shear and moment, right? So beams are long, slender members, and they typically resist loading that is perpendicular to their longitudinal axis. And that's usually gravity load, right? So when we have this loading perpendicular to the longitudinal axis, the beam develops both shear and moment. And this is why we draw shear and moment diagrams for our beams. We often want to know what the maximum shear and maximum moment are that form within those beams, right? Shear is the result of transverse shear stress distribution that acts over the beam's cross-section. So I have this image for you here, which is from Hibbler, the book Hibbler, and it shows you the distribution of shear along the cross-section of a beam. So if we were to make a cut on a beam that's loaded perpendicular to the longitudinal axis, we would see the distribution of shear would look something like this, okay? Now, due to the complementary property of shear, this stress will create corresponding longitudinal shear stresses, which will act along the longitudinal planes of the beam. So here we have this element. We're zooming in on this element, and you can see we have transverse shear in this direction on the face of the element, and we also have this longitudinal shear that occurs in the longitudinal axis of the element. And this here represents tau, the shear stress. Okay, so let's kind of go through this example to better understand shear stress and kind of put it in context in the real world, okay? Let's consider the following two examples of beams, right? So on the left here, we have an image of kind of what looks like a beam, but really you can think of this as a bunch of wooden boards that are not connected to each other. They're not bonded. When we load those wood beams or those boards with some load P, you can see that those sides, they kind of slide relative to each other as the beam deflects due to the load P. Okay. This second image here on the right shows those same three boards, but the only difference is you can think of that we've like glued those boards together, or we've bonded them together somehow. Now they act like a beam. They act as one long, slender member that is, they're all resisting that load P as it's applied perpendicular to the longitudinal axis. And now we can consider the longitudinal shear stress that acts between those boards. So what is the shear stress that's acting between those boards that basically is preventing these boards from sliding and acting now as a beam, as one single structural member, as one single unit. As a result of the shear stress, we also now incur shear strain that develops, and that this distorts the beam in a complex manner. So we are going to discuss shear stress in this context, and we also know that it corresponds to shear strain, right? Stress and strain can be connected to each other through Hooke's law, okay? We're going to go over Hooke's law in a different video. So with that information, let's now go ahead and kind of do a quick derivation, because this is a review video, so we're not going to go into too detailed of a derivation, but I want to go over a quick derivation with you where we can come up with the shear formula, okay? So we're going to start with drawing just a simply supported beam. And what is a simply supported beam again? We have a pin support on one side, we have a roller support on one side, and then we have some loading on the beam. I'm going to draw a constant distributed load across this beam. Okay. And of course, if I have some constant distributed load, let's say this is W, I have some reactions that occur at both of the supports, right? Now what am I going to do? We're going to do what we always do when we're deriving these formulas. We're going to make a cut, okay? And if we make a cut along this member, what happens whenever we make a cut? We expose the internal forces. What internal forces do we expose? We have shear, V, and we have moment, M. We also have internal axial force, but since we don't have any load in the X direction, I'm not going to draw the axial force N right now. So I'm just going to focus on V and M because those are the two internal forces that I do have, right? We know from the flexure formula that sigma is equal to MC over I, and there's also another video that already derives this equation for you and shows you an example of it. So if this is unfamiliar, make sure you go back and review that example, okay? This equation shows that sigma, the normal stress in this member, varies linearly along the length of along the cross section of the element. So now we want to know the same thing. We want to say, well, if moment causes normal stress, and this varies linearly along the face of the element at the cross section, what does the shear do? Well, it causes shear stress, right? Moment causes normal stress, sigma. Shear causes shear stress, okay? So we're going to relate this shear force V to tau. This is the Greek letter tau, which we denote for shear stress. Okay. If this normal stress varies linearly, I'm going to show you, or Starvation will show you, this is a parabolic distribution. It's a little more complex. Okay. So let's go ahead and continue here. Let's say we're going to continue kind of discussing this beam element, but I'm going to make this a little bit more general here, okay? I'm going to make this a little bit more general, and I'm going to draw a beam that has some variable loading. Doesn't have to be constant distributed. It can be any loading on that member. This is a simply supported beam. And what I'm going to do now when I derive, of course, I'm going to isolate a teeny tiny differential element with some teeny tiny differential with dx. And now I have this cut here, right? I'm making this tiny little cut. I'm going to zoom in on this cut. And I'm going to draw it here for you. Why is it my rectangle forming? Let's try this one more time. There we go. Okay. So if I have this little teeny tiny cut that I'm making, what happens? Well, I've made a cut in the middle of the beam. I have those internal forces. So I have on this left side some shear force, and then I have some moment, and then I have equilibrium. So I have some V on this side, but because my loading is changing, it's V plus whatever the change in V is from one point to another, because remember, this element has a width of dx. And then the same thing goes for my moment. I would have on this side for equilibrium moment, but it would be plus some change in the moment, right? So this is basically what's happening internally if I'm making that cut. And the internal moment is changing as a function of x, okay? So now, if I continue this, okay, if I continue this, and I want to show the distribution on this element, what's happening here, we remember, I have my sigma right, acting in compression at the top, like this, if this were the neutral axis of this member, citizen NA. And then at the bottom, I have tension, and that's pulling this direction, right? So I would have some sigma, I'd have some sigma prime because it's changing. I would have my moment, I'd have my M plus some dm here. This is the same element. I'm just showing you basically what's happening here, because now what I want to do, this is my neutral axis, right? I'm going to make another cut because remember, I want to figure out what's happening in between those boards. Remember, if these were the boards, this is the beam here that we're talking about. I want to know what's happening in this direction. So I'm not going to use this element. I'm going to make a cut along the face of that element now. So I'm going to come here. I'm going to say I want to make another cut. I'm going to zoom in on that cut again. I'm actually just going to copy and paste. Okay. If I have this cut, what happens now is I'm exposing something on the bottom here, and this is tau, my shear stress, right, at this portion. Okay. Now, if I go through equilibrium here, I need to make sure that the integral of sigma across this area, this is my dA, right, my dA, I need to make sure that my integral of my sigma dA is equal to what's happening with sigma prime plus tau, right? I need to make sure that all of these stresses are in equilibrium. Okay? When I go through that derivation, I will add in sigma equals mc over I, or my over I, all of that good stuff, and I will be left with this equation here after I go through equilibrium, and I will get tau equals bq over I, b, and I'm going to go through what each of these are. Okay, this is my shear stress formula. Now, let's go ahead and define each of these terms. So, what is tau? We know that is the shear stress, right? Okay. What is V? That is the shear force. Okay, remember, that's the internal shear force. Stress is internal. We use internal forces to calculate it. Now, what is Q? Q is actually the first moment of area about your neutral axis, and we use the symbol Q for this. The actual definition of Q is the integral of y over the area, and this is the first moment of area, and this is the first moment of area about your neutral axis. I, this is the moment of inertia. And B is the width of your section at the point you're calculating the shear stress at. Okay, now when we go over an example, I'm going to show you how to calculate Q, how to calculate I, how to calculate B, and how to calculate T. Okay, let's go ahead before we go through the example and just quickly cover the limitations of the shear formula before we go to that example. So, one of the major assumptions that we make when we're developing the shear formula is that shear stress is uniformly distributed over the width T at that section, okay, or the width B actually at that section. We're using T or B, it's the same thing. This assumption basically means that the average shear stress is calculated across the width, okay? Typically, this assumption holds less true as your B to H ratio increases. So B is the width to the height ratio. As it gets larger, this assumption becomes less true, okay? But this isn't a huge problem because usually the shear in our beam is not what's going to govern our design. It's typically the bending. So there are also a lot of factors of safety in place that make it that this assumption is typically okay to use and check for when we're designing. The next part of the assumption here is that this formula will not give, or not assumption, limitation now, is that this formula gives inaccurate results at the junction between the flange and the web of I-beam. So that would be these points right here. We're not going to use this formula to calculate the shear at those specific points where the width changes suddenly from this small to this large, okay? We have something called the stress concentration, so we'll have another formula in the code that we can use to give us a little factor that we can multiply, and then we can apply that formula there, okay? But we're not going to directly apply the formula for shear stress when we are trying to calculate the shear stress at that junction, okay? Again, fortunately, these limitations are not a huge problem in engineering practice because most of the time engineers are interested in calculating the average shear stress, okay? And this occurs usually at the neutral axis, where the B to A width ratio is very small, okay? So usually it's not a huge problem, and we go ahead and still check for shear stress or calculate the shear stress using this formula, okay? But it's always good to know the limitations when you're using any formula, and it's also good to know where everything came from. All right, now that we have gone through our mini derivation and we've talked about some of the limitations of the formula, let's go ahead and try an example. Basically, what we're going to do is we're going to find the maximum shear stress in this member. So I'm going to write down the problem here. Tau max shear stress, okay? I'm going to start by drawing a beam, and this beam is simply supported. And I'm going to put a constant distributed load on this beam. And I'm going to give this a value of W equals 200 pounds per foot. And I'm going to call this point here A at the pin, point B. And I'm going to go ahead and, also we have 8 feet that we're dealing with. 8 feet, okay. I'm going to go ahead and draw the resultant here. 200 times 8 gives us 1,600 pounds. This is a symmetric beam. That means I'm left with 800 pounds in the vertical direction on each side. Okay. Now what we're going to do is, let me draw the cross section for you. We're dealing with an I-beam here. Okay. And this is a cross section. So this is all given in the problem. And then let's put some dimensions here. So we have 8 inches at the top, 2 inches here, 8 inches, 2 inches, and then we also have the width of the web here. As 2 inches. Okay. Now, the first thing I'm gonna write out the formula that we're using here. So we're using tau VQ over IB. Okay. Now, let's go through what we need to figure out. We need to figure out V, Q, I, and B. Moment of inertia, you should know how to do already, and we're going to go through that formula. That is from calculus. There should also be a review that kind of goes through that a little bit more. The B is just the width of the cross section at the point you're trying to find the shear at. V we can get from the shear diagram. And Q is another geometric property similar to I that we're going to go over, okay? So let's start by calculating V. Let's go ahead here and draw the shear diagram that corresponds to the loading. So I'm going to go up to 800. I have a constant distributed load, so I have a linear shear diagram. I'm going to push up to 800 here. And this is my shear diagram. This is 4 feet. This is 4 feet. Everything is symmetric, super easy. And we notice here that the max shear is at the supports. That's not always the case, of course. It depends on the loading. So you need to draw the shear diagram to make sure that you're getting the max shear force, okay? Now, the max tau occurs, I'm going to come back up to our derivation to kind of talk about where does the maximum shear stress occur. So, remember, we had talked about how the normal stress is distributed. It varies linearly across the cross-section of the element. Well, what about the shear stress? I mentioned to you that it was parabolic. So this is a profile. The shear stress varies in a parabolic manner. And this is my neutral axis. So where would the max shear stress occur? Right? This is the distribution. Max shear stress occurs here. at the NA. Recall the profile for bending stress for normal stress due to moment, right? Okay. What is the sigma at the neutral axis? It's 0. So at the neutral axis, your sigma, your normal stress is 0, but your tau is maximum. That is very important to remember. Now, this problem is asking for the max tau. So where am I going to calculate tau at? At the neutral axis. Where is the neutral axis of this cross section? Smack dab in the middle because it's symmetric. So, where is the neutral axis? Right in the middle. Okay, right in the middle of the section. Okay, so let's continue. We have our V value done. We need Q, I, and V. Okay, I'm going to work on I now. So let me go ahead. In the video I go over for normal stress due to bending, I use the parallel axis theorem to calculate moment of inertia. Because I used the parallel axis theorem in the other video, in this video I'm going to show you a different method that you can use to calculate moment of inertia for certain shapes. So, because the neutral axis, right, acts at the center of this shape, I can use something called the cutout method. The cutout method says I can draw a box and I can find the moment of inertia of the whole box minus the moment of inertia of these little inner portions. I'm going to call them the holes, okay, or the cutouts. So what I'm going to do, what is the moment of inertia for a rectangle? 1 over 12 BH cubed. Okay, this cutout method only works if the center, the neutral axis, is in the middle of the cutouts and the shape. And in this case it is. So, for example, this does not work for a T-shaped cross-section. Right? Your neutral axis would be somewhere here. That is not the middle of the cutouts. Does not work for a non-symmetric cross-section. It only works for these symmetric ones. Okay? So, let's go ahead. The moment of inertia at the neutral axis is equal to 1 over 12. I'm going to do the big box. 8, 12 cubed. Minus the cutouts, I have 2 boxes, times 1 over 12, times 3 times 8 cubed, and I am left with 896 inches to the 4th. Okay, now, what is the Q value? Q is equal to the sum of all of the little areas times the distance from the middle of that little area to the neutral axis. What does that mean? I'm going to show you. Hopefully this is a refresher, okay? Q, I'm going to go ahead and copy this image again. Okay. Now, we know that Q is equal to the sum of A, Y bar prime. So we're going to split this up into 3 sections. This top section, section 1. This middle section, section 2. And the bottom section, section 3. Okay, now let's go through each one of these. Equal to, let's do the top and the bottom section. They are equal in area. So I'm going to do these together. 8 times 2, that's the area. Okay, I'm going to put a 2 outside because there's 2 of those, right? There's 1 and 3, they're the same. So I'm going to put 2 outside. What is the Y bar? The Y bar is the distance. Doesn't matter which one you pick, it's symmetric. From the middle of section 1 to the neutral axis. So, half of section 1, you get 1 inch from here, you get 4 inches from there. This is a total of 5 inches. That is my Y bar prime 1. 5 inches. Plus, what is the area 2? The pink section. That is going to be 4 times 2. And what is the Y bar for that area? Pick a different color I haven't used somewhere in here. The distance from the neutral axis to the middle of that section. So if I'm at the neutral axis, I'm going to pick this portion of that section right in the middle, okay, and take the distance of that section to the neutral axis. That would give me 2 inches, okay? And if I solve for this, I get 96 inches cubed, okay? That is how I calculate my Q value. Now, what is the T value? Well, I want the T value at the neutral axis. So the thickness at the neutral axis is 2 inches, okay? And I think we have everything we need now. So let's put all this together. Tau equals VQ over IT. I got V from the shear force diagram, 800. I got Q of 96 inches cubed, this is pounds, divided by I, which was 896 inches to the fourth, 2 inches. And if I solve for all this, I get tau max is equal to 42.86 psi, pounds per square inch. Okay, that is the end of this example problem. Here is a practice problem for you to try on your own and see if you are able to apply what we learned in this video today to solving this problem. I'm Dr. Munji, and I hope you enjoyed this review of shear stress.